This lesson is going to be pretty straightforward. We only have one objective of being able to identify the 8 different parent functions. This lesson in and of itself is really more so the foundation for lesson 10. A lot of the things that we see in this lesson, a lot of the functions that we're going to learn about in this lesson, we will then do things with in lesson 10. So all we're doing in lesson 9 is learning about 8 different functions. We're going to complete some tables and graph those functions and talk about some properties of them. So starting with our first function, the absolute value function. So I've given us a table with x values here. We're going to plug these x values into the y value, into the equation to get the y value out, and then we're going to plot the points and see what the graph looks like. So plugging in -3, the absolute value of -3 is 3. Plugging in -1, the absolute value of -1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. And the absolute value of 3 is 3. So just to be clear, when we plugged in -3, we got out 3. So we're going to go plot the point -3, 3, plot the point -1, 1. We're going to plot 0, 0. We're going to plot 1, 1, and 3, 3 after we set up some axes on this coordinate system, and then we'll be able to see what the graph of the absolute value of x looks like. As you set up your axes, do make sure that you label both your x and your y axes. In lesson 10 specifically, we're going to be doing a lot of graphs. And really in this unit, we're going to be doing a lot of graphs. And every time we graph something, you need to make sure that both your x and your y axes are labeled. So now I'm going to go start plotting these points. I'm just going to go by ones. So here is -3, 3. There's that point. The point -1, 1 is right here. Here's the point 0, 0 at the origin. Then we have the point 1, 1, and we have the point 3, 3. Now I'm going to connect these points so that we see the graph of the absolute value of x, and that graph is a V-shaped graph. So that's important because I could understand how maybe if you were just looking at these points and you didn't know that the graph was V-shaped, that you might try to connect those points into a U shape. Right? You see how this is more rounded out? That would be incorrect. The absolute value function does not round out. It is 2 lines that meet at the origin like this, okay? And that's important, and we'll see why that's important when we start applying transformations to these graphs, but we need to know that the absolute value function is shaped like a V. Let's talk about the domain of this function. Domain, we learned about domain back in lesson 3. When we look at the equation of the absolute value of x, there's no denominator, there's no even radical. The domain is all real numbers. We can also see that on the graph. Notice that when I connected these points on the graph, that's 1. I didn't just do this and stop, right? Because even though 3 was the largest x value in the table, I could have plugged in, say, 7, and I would have gotten a point up here at 7, 7. So the graph does not stop. So I do have arrows on both ends of the graph. And so even with those arrows, we can see that the domain is all real numbers. The range deals with y values. The smallest y value on this graph is 0, and it is included. The graph does not go under the x-axis, and the range goes all the way off to positive infinity because the graph continues to go up. The x-intercept and the y-intercept are the same point of 0, 0. Now for the square function, I'm again going to just take these x values that I already have in the table and plug them in to this equation to get the y values out. There's nothing special about the numbers that I picked here. I just picked some numbers that we can plug in and get some points out. Okay, so if you were trying to do this from scratch, it really wouldn't matter what x values you put here as long as the domain of your function is all real numbers, which it is because we have no denominator and no even radical. So taking -3 and squaring it, make sure you write parentheses around that when you square it. You do need to use parentheses when squaring a negative number because it gives you out a positive number, because a negative times a negative is a positive. So now that we have these y values out, now we're going to do the same thing we did before. And we're going to set up and label our X and our Y axes, and we're going to plot these points so that we can see what the graph looks like. I'm going to move my X axis down here because my graph does get up to 9 on the Y values, and I want to make sure that I can plot those points. So I just chose to move my X axis down, because if you notice, we don't have any Y values coming out that are negative. Do label both your X and your Y axes. I'm going to plot the point -3, 9. So I'm going to go left 3 and up 9. I'm going to plot the point -1, 1. So I go left 1 and up 1. Plot the point 0, 0 at the origin. 1, 1 and 3, 9. So here's the point 1, 1. And then here's the point 3, 9. And now I'm going to connect these points. And when we connect these points for the square function, these are actually, this graph is U-shaped. This graph is shaped like the letter U. So the word function should really be over here. It's just some weird formatting. But this is in fact U-shaped. So the absolute value function is V-shaped and the square function is U-shaped. Looking at the graph, the range is 0 to infinity. Smallest y value on that graph is 0. The graph does not go under the x-axis, and the graph has both an x-intercept and a y-intercept at the origin. The next function we have is the linear identity function. We're going to plug in our x values into this equation and get out our y values. The equation tells us that y is equal to x. So whatever we chose for x is the same thing that we're going to get out for y. Keep in mind, I could have added 6 to this table and I would have also gotten out 6. I could have added -4 to the table and I would have gotten out -4. So please don't think these are the only points on the graph. Okay, the graph is going to continue on forever in both directions, because what we learned back from lesson 3, even just looking at the equation, y is equal to x, that has no denominator and it has no even radical. So the domain of that function is -infinity to +infinity. We should always be able to tell domain even without looking at the graph. Range, you have to read off the graph. So the range, we need to graph the function first, really, before we can see what the range is. So now I'm going to start plotting these points. I'll plot the point -3, -3. From this first one here, -3, -3 is right here. Plot the point -1, -1, 0, 0 at the origin, 1, 1, and then the point 3, 3. And then I'm going to, so again, what I was saying with the bottom 2 points is that the point 6, 6 is also on the graph, for example, and the point -4, -4 is also on the graph, for example. So these points connect and form a line. I'll just make a note here. Notice y equal x is in the form of y equals mx plus b. We can see that m, the slope of that line, is 1, and b, the y-intercept, is 0. So let's go ahead and fill in the x and the y-intercept, which I'm just reading off the graph, right? The only place the graph touches the x and the y-axis is at the origin. And the range is -infinity to +infinity, because this graph goes down forever and it also goes up forever. So every single y value is in the range. Next, we have the constant function, and next to the constant function, we're told to choose any number for b. So for example, I can choose b to be -2. Then my equation is y equals -2. No matter what value of x I plug in, we will always get out -2. The equation does not depend on x. The equation only depends on y. In fact, we've seen equations that look like y equals a number before, from the lesson where we first learned about lines. If we have a equation y is equal to some number that is a horizontal line, the graph of that looks like this horizontal line going through -2 on the y-axis. It has a domain of all real numbers. Its range is the single number -2, right? That's the only y value that's on the graph. So, but I don't want to write this because really it's not always going to be -2. It would be whatever value you chose for b, right? Because I could have easily chose b to be 6, and my constant function would have been y is equal to 6, and then the graph of that would have looked like a horizontal line going through 0, 6, and that would have been my the only number in my range, and that also would have been my y-intercept. Generally speaking, a constant function, most of the time the x-intercepts are none, unless it is the function y is equal to 0, which would be the x-axis where everything would be an x-intercept, but we won't be dealing with things like that, so we don't have to worry about that. But for the most part, unless you choose your constant to be 0, the graph does not have any x-intercepts, right? Like this line of the graph here is not touching the x-axis, the same way that this line down here is not touching the x-axis. Okay, so for the y-intercept, generally speaking, the y-intercept will be 0, b. Remember, you get the y-intercept by plugging in 0 for x, and what we get out is b. So there's our y-intercept. Next, we have the cube function. I'm going to go ahead and take these x values and plug them into the equation so we can see what the graph, what points we get, so we know, so we can plot those points to see what the graph looks like. First, I'm going to plug in -2. So we're taking -2 and we are cubing it. So just to make sure we're all clear about that, we're doing -2 times -2 times -2, which gives us a -8. Next, I'll take -1 and I'll cube that. -1 times -1 times -1 is -1. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So now I'm going to go ahead and set up and make sure to label my x and my y axes. And then we're going to start plotting these points so we can see what this graph looks like. Now this graph goes up to, at least our points go up to 8 and down to -8. Right, like we have the point -2, -8, and we have the point 2, 8 down here. I'll go ahead and label the other ones. So I'm going to probably do my y-axis by 2's. Yeah, I'll just do my y-axis by 2's. I'll say that this is 2, 4, 6, 8, -2, -4, -6, -8. And I'll just do my x-axis by 1's. So this is 1, 2, 3. So let's plot these points. So we have the point -2, -8. So here's the point -2, -8. We have the point -1, -1, which would be about there, because -1 would be somewhere in here. We have the point 1, 1 right there. Or skip 0, 0, we have the origin. And then we have the point 2, 8 as well. And these points connect to look like a swiggle of sorts. They look like this when we connect them. That general shape there. So this graph is generally shaped something like that. The domain of this function is all real numbers. There's no denominator. There's no even radical. The range is all real numbers. The graph goes down forever and up forever. And the graph has both an x-intercept and a y-intercept at the origin. Next, we have the square root function. First things first, let's start off with the domain of this function, because when we look at the square root, I hope everyone can see that that is an even radical. Right, I'll just write it here. Y is equal to the square root of x. That's an even radical. And going back to where we learned about how to find the domain, how we find the domain of an even radical is we take what's under the even radical, which is x. We set it greater than or equal to 0, and we solve. There's nothing to really solve here because the x is already by itself. So taking x greater than or equal to 0, 0 is included, and we're shading to the right on that number line. So this goes from 0 to infinity for that domain. So, which makes sense because if we start filling out the table, the first thing we have is the square root of -1. We know that we can't take the square root of negative numbers, right? No one should be telling me that that's I. Yes, it is, but we're graphing this. We're talking about what's happening in the real number system. this is undefined. So we won't get a value out, which makes sense because the domain starts at 0. So the smallest x value we can plug in is 0. So I'll go ahead and plug 0 in. When we plug in 0 and take the square root of 0, we get 0. The square root of 1 is 1. If you notice, the numbers that I chose in this column here, my x values, I intentionally chose numbers that were perfect squares. So the square root of 4 is 2. The square root of 9 is 3. And I just did that because it avoids us getting things like the square root of 5 that we would then have to put in the calculator to approximate. So I'm going to move my y-axis back here because the domain does not have any negative x values in it, so we don't really need a lot of negative space on that x-axis. Do make sure and label both your axes. I'm just going to go by ones. The first point we have is 0, 0. Then we have the point 1, 1, followed by 4, 2. And then this is 5, 6, 7, 8, 9, goes up to 3. So I'll connect these points. This graph looks like this. That's the general shape of the graph of the square root function. Now that I can see the graph, I can see that the range is also 0 to infinity for the y values, and the graph has both an x-intercept and a y-intercept at the origin. Next, for number 7, we have the reciprocal function. For the x values that I chose for this table, I intentionally chose numbers that when we take the reciprocal of, we'll get something out that is at least easy to work with. So all that this function does is you plug in an x value, and what comes out is the reciprocal of that x value, the flip of that x value. So for the first x value we have in the table of negative 1/10, when I plug that into the function, we get out negative 10. It flips negative 1/10. If another way to see that is we would have 1 over x, x is negative 1/10. So we have this here. We know that the fraction of 1 in the numerator is just a 1 over 1. We have a negative 1/10 in the denominator, and we know we divide fractions by keep, change, flip, then multiply straight across the top and straight across the bottom to get negative 10. So again, only thing that happens for your y value is you're just getting the reciprocal of your x value. For negative 1, its reciprocal is negative 1. For 0, we cannot take the reciprocal of 0. The function is undefined when x is equal to 0. 0 is not in the domain. The reciprocal of 1 is 1, and the reciprocal of 1/10 is 10. Before we go and graph the function, label your axes, let's go talk about the domain very quickly. This function, or this equation, this function, y is equal to 1 over x, it does have a denominator. We learned about domain, finding the domain of a function with the denominator. You take what's in the denominator and you set it not equal to 0. So on the number line, we're saying that we can have any real number except for 0. Whole in the number line at 0. This is what the shading would look like. It would be everything from negative infinity to 0, and then everything from 0 to infinity. So we can see that 0 really is undefined. Now I'm going to graph this. I'm just going to say, I don't know what this is going by, 2, 4, 6, 8. Yeah, let's go by 2s on our y-axis. So this is 2, 4, 6, 8, 10. And then this is negative 2, negative 4, negative 6, negative 8, negative 10. And I'm actually going to move my 2, 4, 6, 8, 10 to the other side. Okay, so let's start plotting points. Negative, and I'm going by, I will say that this is, I'll just say that this is 1, right? That this is negative 1 and that this is positive 1. And this graph, the scale does seem very weird, but we'll talk about that in a second. So I'll start plotting points here. I'm going to use a different color. Negative 1/10, negative 10 is going to be somewhere around here. Negative 1, negative 1 is going to be somewhere right there. And then 1, 1 is going to be about No, 1, 1 will be here. And then 1/10, 10 will be somewhere over here. Okay, so we just have those 4 points right there plotted. We could very easily like pick other values in here, like pick 1/2. For instance, if you plug in 1/2, you'll get out 2. If you plug in different value, things like that to get more points in the middle. But what's important in this lesson is us being able to identify the shapes of these functions, and the general shape of the reciprocal function looks like this. There's one piece of the graph that comes in quadrant 1 and curves like that. And then there's a second piece of the graph that comes in quadrant 3 and goes like this. So the reciprocal function, its graph consists of 2 separate pieces. What's happening in the middle, remember, 0 is not in the domain. Later on in this course, we will learn that what's happening on the graph is that there is a vertical asymptote, which for now I will just abbreviate as VA. That stands for vertical asymptote, that is happening at x is equal to 0. But for now, we don't really need to know that. What is important that we know now is that the graph of the reciprocal function is those two blue pieces together. So without all the mumbo jumbo in the background, what the graph looks like is this. One piece on that side, one piece on that side. Let's talk about the range. The range is all real numbers except for 0. That graph never touches the x-axis. You see how these have this blue piece here that's leveling out. The graph is never going to touch the x-axis, and the same thing is happening as it goes up. It levels out as it along the y-axis. So there are no x-intercepts and there are no y-intercepts. There is no y-intercept. The last function we're going to look at is the cube root function. I'll start by filling out the table. The cube root of -8 is -2. The cube root of -1 is -1. Of 0 is 0. Of 1 is 1. And of 8 is 2. And again, I'm just using that. This is not something that you necessarily need to know, right? What is important in this lesson is that when you look at the graph of the function, you're able to tell me, oh, that came from the cube root function. So let's go ahead and start plotting these points. I have the point -8, -8, -2. So here's -4. So it looks like I've just ran out of space. Here, if this is -4, -8 would technically have been like right here, somewhere over there. So I'm just going to stick -8, -2 right there. There's -2. Here's -1, -1. Put that there. There's the origin 0, 0. Here's 1, 1. And then the point 8, 2. There's 4. There's 8. Here's the point 8, 2. So I have all these points plotted here. The graph looks like this. It looks like a swiggle, but it's a lot wider than the swiggle we saw before. So generally speaking, the graph of the cube root function looks like that. It kind of looks like it's leveling out, but it's not really. The graph does continue to go up higher and higher and higher, and to go lower and lower and lower and lower as it continues to stretch outward. No denominators and no even radicals. That is an odd radical, not an even radical, so it doesn't give us any problems. The range is also all real numbers. Graph goes up forever and down forever. And the graph has an x-intercept and a y-intercept at the origin of 0, 0. So big picture from this lesson is that these 8 different functions, we should know the absolute value function is shaped like a V. We should know the square function is shaped like a U. We should know that the linear identity function is a line with slope 1 and a y-intercept of 0. The constant function is a horizontal line. We should know what the general shape of the cube function is, that it looks like this swiggle. We should know the general shape of the square root function, that it looks like this arch that starts right there, right? Nothing else exists to the left of it. The reciprocal function, we have these 2 separate branches of the graph, and then the cube root function, we have this swiggle shape down here.